and we're eager to hear what you have to say from information theory to robust Bayesian statistics.
Well, thank you, Andrew, for this very nice introduction. I'm really enjoying the conference because it's very nice. I can pick up ideas from different areas. And being here is I feel very honored to be here and give this talk, especially in this beautiful building on top of this tower, close to the sky. And I can't help thinking, that's what it is to be in heaven. Okay, sorry, that's French humor. Okay, this picture was taken by Lucien Birger in 1994. I like it. I think it's nice. At this period, so Andrew was working with Pascal Massin and Lucien Birger on a paper which is, I think, called Risk-Bound via Penalization for Model Selection. And it was a big hit, in France. I remember at that time, everybody was doing model selection with penalized criterion to design adaptive estimators, and I was no exception. As you said, I was doing my PhD on this topic, and I was very honored that you accepted to review it. Not only you were a member of the committee, but you accepted to review it. And today, so 30 years later, I will not at all talk about frequentist estimation, but I'm going to move to a topic which I do not master completely, which is Bayesian statistic. And I will want to propose a surrogate, a substitute to the Bayesian posterior distribution, which is actually quite challenging after we've seen the talk of i.i.d. So I have to motivate this. So in order to motivate that, probably the best thing to do is just to recall a few facts about the classical Bayesian paradigm and some of the properties of the posterior distribution, Bayesian posterior distribution. So my problem is about estimating the distribution of data. So I assume I observe n-i.i.d. random variables, and I assume these random variables are i.i.d. with a distribution, common distribution, which is unknown and that I want to estimate. And to achieve this goal, I have to consider a statistical model, which can either be parametric or non-parametric, whatever. At least it is parametrized, so I have a parameter space. And so I can say that my true distribution, if it is in the model, can be written as a P with respect to a theta star that belongs to my parameter space. So I want to estimate theta star. And what I have in addition to that, because I'm in the Bayesian paradigm, I have a prior on my parameter space. And this prior gives me some hint on where the parameter theta star is likely to be or unlikely to be. And because of this prior, there is an interpretation, which is probabilistic, that says that everything's as if my parameter theta star has been drawn according to the prior distribution pi, and my data, what I observe, the distribution of my data is just a conditional distribution, knowing the parameter theta star that I don't know. And what you can do if you want to have some information on theta star, just to reverse the conditioning. So what you do is you just build up the posterior distribution of the random variable theta star, knowing the data, and you end up with a distribution, which is called the posterior distribution, Bayesian posterior distribution, which is denoted by a B here. That gives you some hint on the location on theta star. And I like to think of this posterior distribution in the following way. For a long time, I've been doing frequentist statistics, which means that every time I wanted to design an estimator of theta star, I had to choose a deterministic function of my data to estimate this theta star. It means same data, same estimator, same value for the estimator. But in the Bayesian paradigm, what I can do is I can just use this distribution that depends on the data in order to pick up one point at random And that would be my estimator. That would be some kind of randomized estimator. And what I want to know, if I do that, is my point close to my target? Is my point close to the theta star? That's what I want to do. So this is why a lot of people in the area have tried to find the sets which concentrates most of the mass of this posterior distribution here. And it is quite, there's a very nice result in this direction that probably most of you know, which is in the setting where the statistical model is parametric. So when the statistical model is parametric, which means that the parameter space is a subset of Rk, and my statistical model is very regular, and I have a nice prior on it, which puts math almost everywhere, then you can prove that if you pick up one point at random according to this posterior distribution, then if n is large enough, then the point you will get will belong to an ellipsoid, which has a certain shape and a certain size. And the shape of the ellipsoid will be, actually, the ellipsoid will be centered at the maximum likelihood estimator. So it's nice because it bridges the Bayesian point of view with the classical frequentist point of view. The axes of the ellipsoids will be given by the eigenvectors of the Fisher information matrix. And the size of the ellipsoid will be proportional to 1 over square root of the number of data you have. And it also depends, of course, on the dimension k, the number of parameters you have in your statistical model, and on the level of confidence you want to have on the result. So this is typically what you have in a parametric case. So that's a very nice result. And so the question, why do I want to propose something else for the Bayesian posterior distribution? I want to propose something else because when you want to analyze the Bayesian posterior distribution, you get very nice results under the assumption that the data are drawn according to a distribution that belongs to the statistical model that you have chosen. But if it is not the case, then things can go wrong. And it's not very difficult to find very simple examples where you have, let's say, 1 million of data that are drawn according to your model. But you just add one additional point to your data with a different distribution, and everything can go wrong. I mean, the posterior distribution can behave very poorly. So there's some kind of instability here, and this is exactly what we want to solve. So this is why, in order to be more specific, I'm going to do as if I wanted to do classical Bayesian statistics. So I start with a statistical model that can be parametric or non-parametric, and I want to propose another posterior distribution that will depend on the data, but will not be the classical Bayesian one. As you will see, it will be just a slight modification of it. And of course, what I want to do is to keep or retain some of the nice properties of the classical Bayesian posterior. I mean, at least when the model is exact. For example, in a parametric case, I would like to say, well, I can also concentrate on an ellipsoid of the same shape and the same size. But I want to relax the assumption that my data are truly i.i.d. with a distribution that belongs to my statistical model. Because in real life, every time you have to design a model for your data, you cannot be sure that the model is exact. All you can expect is that it gives you some kind of good approximation of the truth. And so I don't want to assume that my data are i.i.d. Maybe they're just independent. And even if there were i.i.d., maybe the distribution does not belong to my statistical model, but lies close to it. Okay, and what I would like to do, and that's because I have some pieces of advice from Andrew, I would like to give some kind of non-asymptotic theory for that, and also to calculate numerical constant. Sorry, that will not be very small, but the best I could do. Okay, so because of this problem I want to solve, I'm going to move from the old or the classical Bayesian paradigm to a new paradigm, which is I don't want to assume a lot of assumptions. I probably very few assumptions. I just want to assume that my data are just independent. And so because I'm not assuming they're i.i.d, it means they possibly have different marginals, p1 star, p2 star, pn star. And this is the only assumption I want to do. And now what I have to do and explain is what is the posterior distribution I want to introduce and build. So it is a construction in 3 steps. And the first step is very, very important. The first step is how can I design a test statistic that will allow me to compare 2 parameters in my parameter space in the following way. I want that if most of the marginal distribution of my data are close to the distribution p theta prime, or closer to the distribution p theta prime as compared to p theta, I want this test statistic to be large. And if it's the other way around, I want the test statistic to be small. So if you think of the Neumann-Pearson test statistics, the Neumann-Pearson test statistics allows you to compare if your data are i.i.d with a distribution which is either one or the other. But it's not what I want to do. I just want to know if most of the marginal distribution are close to one or close to the other. So that makes a little difference. So this is some kind of robust test statistic. And if you look at its definition, so you can forget about the 1/500, it is also based on the densities. I do the ratio of the densities of p theta prime and p theta. And if the function psi here were a logarithm, that would be the log likelihood ratio test. But that's not what I'm going to do. I'm not going to take the logarithm. I'm going to change it into this function phi. And this function phi is actually close to the logarithm in the neighborhood of 1. But the main difference with the logarithm is that it is bounded. It takes its value between -1 and 1. It cannot go to -infinity nor to +infinity. So in a certain way, we clip. So because of the properties I've just described, what I'm going to do in the next step is just take the average of this statistic with respect to some kind of Gibbs measure. So for those of you who are familiar with some kind of Gibbs measure, it actually tried to mimic a maximum. So I integrate this with respect to theta prime and the prior half, and I introduce this Gibbs measure, and this some kind mimics the maximum of my test statistics over all possible theta prime. That's what you should have in mind. So there are only 2 situations. If this integral is large, it means that there's somewhere in my parameter space a theta prime for which p theta prime is a much better model for marginal distribution of my data than p theta is. If this integral is small, that would be the other way around. That means there is no such theta prime. And so I can associate to each parameter theta in my parameter space a score that gives me some hint whether p theta is a good model or not a good model for my data. And the natural idea is then to say, well, I want to concentrate my posterior distribution over those theta for which this is small. And so this is why we introduce some kind of Gibbs measure and the other way around. If you take the function psi, not to be the one here, but a logarithm, then, or proportional to a logarithm, I don't remember the constant, then you will end up with a classical Bayesian posterior distribution. So it's not something that is completely different. You're just replacing the log into something which is bounded. Okay, and what I want to do now is go to a theorem. No. For some specific constant. If you take another constant, you will end up with a fractional Bayesian distribution, which also some people use in order to have more robustness. So I don't remember the constant you have to put, but there's one constant with the log, and you get the classical Bayesian posterior distribution. Because Andrew told me I have to calculate numerical constant, and that actually it's not true for any constants, what I'm going to show. So you have to calibrate the constant in such a way that you get to the result. Actually, you can put a constant that would be smaller, but I will show constant that might be higher. So, well, this works. What do you mean? These are the densities in my statistical model.
Oh, okay. So each one is parameterized.
Yeah, it's parameterized. The model can be parameterized.
Each one is a different function.
This one is a different function, yes. Yeah, yeah. And in order to introduce the theorem, I need to explain two things. I need two ingredients, actually. One is I need to describe what would be a neighborhood in my statistical model, in my parameter space. So I need to describe a neighborhood. And I would need to describe a size of the neighborhood. So I would need two ingredients. And as you may imagine, the size of the neighborhood will be related to the dimension of my parameter space in some way. So I will have to explain maybe a little bit what the dimension is. Actually, maybe I will keep a bit this part, not to be too technical. So for the notion of neighborhood I'm going to use, it is based on the Hellinger distance. So I will say I have a neighborhood, so in my parameter space, I say I have a neighborhood center at a probability P with size R, if I gather all the parameters in my parameter space for which the probability P theta is at a Hellinger distance to P, which is not larger than R.
Is this for the marginal distributions, or is this somehow for the joint?
No, marginal distribution. Yes. Yeah. So this is some kind of trace of a Hellinger ball in my parameter space, okay? I look at all the parameters in my parameter space which are close to my distribution P, for which P theta is close to my distribution P. Okay, and okay, that would be my neighborhood. Sorry? No, okay. And so I need to introduce a notion of dimension and accuracy. So I don't want to be too technical on that point, but there's a funny thing. I mean, when you do statistics in a frequentist way, you have different notions of dimensions, which can be Rademacher, complexity, VC dimension, entropy, and so on. And of course, in the Bayesian world, it's something different that comes out because it's based on the fact that you have a prior. So actually, we measure the dimension of a statistical model looking at a ratio of neighborhoods, of measure of neighborhoods for the prior you have. And you take the log of this ratio. So just to give you some idea what this is related to a dimension, because that's completely not obvious. Just imagine that those balls or those neighborhoods are just Euclidean balls in an Euclidean space. And pi, let's say it's just the Lebesgue measure. So what you calculate here is just the volume of an Euclidean ball in an Euclidean space of radius 2r. And you divide this by the volume of a ball with radius r. So because of homogeneity, this is just 2 to the power of the dimension of the linear space. And if you take the log, you recover the dimension. So you can generalize this into other kind of spaces. So this gives you a dimension, and this is not related to the number of data you have. And you can then design the accuracy at a point p theta in your statistical model, which is given by this formula. So this accuracy, I'm not going to go into much detail, but just to say that if you're interested in how this quantity depends on the number of data, that means if you let n goes to infinity, this will correspond to a rate of convergence toward the parameter theta in your parameter space. And this rate is, if you choose your prior in a suitable way, will give you the optimal rate you can achieve in your statistical model. So you can think of this as a rate when n goes to infinity. And now we have these two ingredients. We have neighborhoods, we have size given by this accuracy, and then we can give a theorem. So the theorem is the following one. So it says that with a probability close to 1, so with a probability 1 minus twice exponential minus psi, if you pick up a point drawn according to this new posterior distribution, then you have a probability at least 1 minus exponential minus psi, so probably close to 1, that this point will belong to this a neighborhood centered at p bar with radius r, and I have to explain what is p bar, and I have to explain what is the size r. So let's start with the situation where the data are truly i.i.d. So this is truly i.i.d. with a distribution that belongs to my statistical model. Then this neighborhood will just be the neighborhood centered at the true distribution of my data. And the radius and the size of my neighborhood will be just the accuracy plus a term that depends on how confident I want to be on the result. And it's not really difficult to prove that if your statistical model is parametric and you have a nice prior, as I've told before, then this neighborhood here will just be contained into an ellipsoid with the same shape and the same size approximately as the one I've shown, which means that we can recover some of the nice properties that we had for the classical Bayesian posterior distribution. The interesting fact is what happens when the data are not drawn according to a distribution which belongs to the statistical model. So if the data are only independent with marginal pi star, then the neighborhood will be centered at the average of the marginal distribution. This is what happens. And if this average, so I could say mixture, if this mixture is close enough to a point in your statistical model, a distribution p theta, then because of this formula here, you will just find that the size of the neighborhood will be of the same order as the one you would have if the data were really i.i.d. with a distribution p theta. So this result here, so you look at here as a point in the parameter space that gives a good approximation of this mixture of the marginals. And you actually try to find a good compromise between approximation and accuracy around this point. And so this result accounts for the fact that the posterior distribution is actually stable with respect to the fact that if you're not in the statistical model, but you lie close enough to it, in the sense that this average is close enough to one point in your statistical model, then you will recover the neighborhood, which is approximately of the same size as the one you would have if you really were i.i.d. So in order to explain a little bit more what is this distance, the Hellinger distance between this mixture and p theta, I've just introduced this inequality here, which is just based on convexity. And let's look at it. So I said that the square Hellinger distance is not larger than that. And if you imagine a situation where, let's say, all my data are drawn according to distribution p theta, except one, which can be an outlier, then it means that in the sum, all the terms will be 0 except 1. And one term will not be larger than 1 because the Hellinger distance is always bounded by 1. So this bound here will not be larger than 1 over n, which means that the Hellinger distance will not be larger than 1 over square root of n. And so this means that what you would get as compared to that is just an additional term which will not be larger than 1 over square root of n, which is the same order as this term. So this accounts for the stability of the procedure. Even if I have contamination, if the level of contamination is not too high, then I will get something which will remain stable. But there is a funny story. I mean, actually, even if none of my marginal distribution belongs to the model, none of them, but the average do belong to the model, which may happen, then this term will be 0. And then I will just recover the same situation, the same size, as if my data were really i.i.d. With the distribution that belongs to my statistical model. Okay, so I just want to point out 2 ingredients of the proof. One is based on the fact that we have a robust statistic, the one I mentioned at the beginning, that allows me to compare 2 points in my statistical model, in my parameter space, in a robust way. And the result I've shown you is based on the Hellinger distance, but you can also find robust tests for other distances, like the L1 distance or Wasserstein or LP distances. You can build those kind of tests as well, and you will get some kind of similar results. And the other ingredient, actually, so it's an inequality that I found in a paper by Audibert and Catoni, which has actually an information theoretical flavor. So this inequality, actually, you want to integrate a function or exponential of a function that depends on 2 variables, u and v. So you take the expectation with respect to v, conditional to u, and you have this inverse. And there is some kind of, this inequality tells you that it's a mixture between Fubini and Jensen, because you change this, so expectation of minus becomes expectation of plus, and the inverse goes outside this expectation. So it's kind of a mixture of those. So I thought when I saw it that it was really based on Jensen's inequality and Fubini, but actually not at all. It's based on the fractional Kullback divergence formula. So it was surprised me, and I think it's a nice result. So with these 2 ingredients, then you get similar theorems for the losses you want to do. So this is some kind of references, and congratulations.
Thanks for your interesting development. Questions? Yes.
Could you comment on computation?
No. No, what I'm going to say is completely probably stupid. So. But I know a lot of people are struggling with the classical Bayesian. I mean, there are all people working on MCMC methods and for calculating those kind of posterior distribution. It's all based on integrals. So what I can say is that because of the law of large numbers, if you do enough simulation, you will be able to do it. But that would be stupid. I don't know. I've never thought of how to implement it so far. But that's quite new. So.
Yeah. Ed?
So, I mean, the results will hold for any parametric distributions that you choose, but do they play a role? I mean, do you get better results with certain parametric distributions for the marginals?
What do you mean better? So, actually, it's not the way I see it. So I didn't comment on that, but beside being robust, which is what was one of the goals, the advantage of the approach is that you can deal with approximate model. And it's important because in approximation theory, this is what you do. You want to approximate complicated functions by something which is simple. So, for example, if you want to estimate a function which is, so your parameter space is non-parametric, okay? It's a class of function, Eulerian function or Lipschitz function. Then it means with this kind of method, you, instead of putting a prior on the space of Lipschitz function, you can just put a prior on a space of parametric function based on linear spaces that will provide a good approximation of this non-parametric class of function.
I have another question. So what if you don't have any messed up observations? They're all, i.i.d. from some distribution, and you're doing this wonderful improvement of maximum likelihood. In maximum likelihood, there's an information projection in the case that the true P is outside of the family. There's a P star.
Yeah.
And you get close to it. Does that persist in this situation? Is there an analog of the Hellinger distance you can use to capture closeness to the information projection or whatever it generalizes to? Something to think about.
Yes, I'm not sure.
Okay. Good. Let's thank Yannick.